Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we're looking at least squares problems. So what are we actually doing here? Well, we're looking at the matrix equation AX equals B that you've seen a million times before. So B and X are vectors and we want to solve for X. We're looking specifically at cases where this system is inconsistent and coming up with a solution that is as close as we can get. So what does that mean, as close as we can get? Well, let's look at this visually. So let's draw this plane here to represent the column space of A. Now, if B happens to be in the column space of A, there will be an exact solution X that solves this equation. It may not be the only solution, there could be infinitely many solutions, but there will be at least one solution X if B is in the column space of A. But if this system is inconsistent, that means we have some B that's outside the column space of A. So I'm just going to put here a point to represent the vector B is outside the column space of A. And sorry for my 2D drawing here, B is supposed to be above the column space of A. So what we want to do is we want to find some vector that takes us from the column space of A to B. Now, if this system is inconsistent, of course, this means that there will not be such an X. If B lies outside the column space of A, you will not be able to find such an X that takes us to our vector B. So what do we do in these cases? Well, we can't come up with a solution, but we may need a solution. So we're trying to come up with a solution that is as close as possible. So what do we mean by that? Well, what we're basically doing is replacing B with another vector, say B hat, that is in the column space of A, because I will be able to find a vector I'm going to call X hat such that A times X hat equals B hat. I know it sounds really weird, doesn't it? We're basically changing the system of equations we have slightly so that we can actually come up with a solution. So to ensure that this solution is as close as possible, this B hat actually needs to be orthogonal to the original vector B. So essentially what we're doing is we're finding the vector that takes us to another vector that is orthogonal to B, since we can't actually get to B if it's not in the column space of A. So how do we go about this? So what we actually know is that this here, this is like our error. This distance tells us how much our solution is out by. So we can write this as B minus B hat. Now that length there, because it's orthogonal, we want that to be orthogonal to this, means of course the dot product is 0. This equation here means that our vector is orthogonal to the column space of A, meaning it must be orthogonal to each column of A. But this in turn means that it will be orthogonal to each row of A transpose. And what that means is we'll have this equation. So A transpose times this vector will give you the 0 vector. So of course, we can just rearrange this equation. Starting by expanding the brackets, we get this. Now remember that B hat is just A times X hat, and then moving this to the other side of the equation, we end up with this. This equation in gold is called a normal equation. So when we can't find a solution to AX equals B because it's inconsistent, we instead solve this equation. So any solution to this equation will be the closest approximation to a solution of this. It will be as close as possible to what we wanted. Okay, let's now look at a couple of examples. So let's look at this example here. I want to find an X such that AX equals B with A and B as they are above. Unfortunately, this system is inconsistent. If you like, you can row reduce the augmented matrix to see that. And that's what you'd expect. I mean, there really is no point trying to use this least squares method when there is an actual exact solution. So what we want to do instead of solving AX equals B, we want to solve A transpose AX is equal to A transpose B. So this will have a non-empty set of solutions. There will always be solutions, and it turns out the solution will be unique if the columns of A are linearly independent. Now in this case, the columns of A are linearly independent because there's only two of them, and the second one certainly isn't a scalar multiple of the first. So we will be able to come up with a unique solution that is as close as possible. So let's just calculate these first. So trying to spare the details of the calculation, we calculate A transpose A and A transpose B, and we've got these two matrices here. So now what we're doing is we're solving the system of A transpose A times some vector X gives us A transpose B. So this matrix here is actually invertible, so there will be a solution to this equation here. Moreover, it will be a unique solution. So in this case, our vector x is just going to be the inverse of this, and then multiplied by the vector b. Once again, I'll spare you the calculations. So this vector x is a least square solution. Of course, it's not an exact solution because there are no exact solutions. Now we're going to check just how close our solution was. So I'm going to get rid of all the stuff down the bottom of the screen. Please pause and copy it down if you need. So the solution I'm proposing is x equals 0.9 minus 0.4. So let's take A and multiply it by this solution that we just have. Once again, I'll spare you for the calculations, but I get this vector here. So it is, I guess, sort of close to our original vector B. To quantify how close it is, we simply take the norm, the length of B minus our solution AX. So putting that on my calculator, I get about 0.5477. So what I'm saying is I couldn't find a vector to take me from A to B because B wasn't in the column space of A. So all those calculations, I found a vector that took me to another one that's close to B. And this is how far it was from the actual vector B. So the point here is there will be no other vector that I can substitute for x that would yield a smaller length than this. There is no other vector that would take me closer to B than the vector I have here. That's what we mean by least squares solutions. All right, let's look at some applications of least squares solutions. So a popular application of least squares is linear regression. So what we do is we have a set of points and we want to find a line that goes through them. So I've written down 4 points, just 4 normal points in our Cartesian plane. You may remember these points, as in the last video I made, we actually found that we could fit a cubic exactly to these points. So they're probably not going to lie in a straight line. Indeed, there is no straight line that goes through all of these points. That's why this becomes a least squares problem. So what we have is a situation where we have our plane and we have points like this on your right-hand side, the red points. They don't lie in a straight line. We want to find a line that is as close as possible to all of the points. What we're doing is minimizing the squares of each of these distances here. Each of these distances here is called a residual, the distance from the line to the point, and we want to minimize those. We want to make them as small as possible. That's what we consider the best line, or the line that's as close as possible. So of course the line will have an equation of this form. I'm just using beta naught and beta 1 because that's what's usually used in statistics. So what we have to do is find the coefficients beta naught and beta 1 so the line is as close as possible to all of these points. So what we do is we set up our matrices like this. Now, apologies for the notation, but I'm going to switch what X means now. So now I'm going to use capital X is going to be a matrix. So when we're doing linear regression, we have a column of all ones, and in the second column, we're going to put all of the X values. So, of course, Y is going to be the column vector with all of the corresponding Y values. Make sure they line up to the X values. And what we're trying to find is this matrix beta, which will have beta naught and beta 1. So I am solving the equation X beta equals Y. So you might be wondering about this column here of all ones. That's just when we multiply them out, I'll get 1 times beta 0 each time. So for example, the first row here by this column here will give me beta naught times 1 minus beta 1 times 4 equals 5. We want that. Each time we want to get an equation of the form beta naught plus or minus beta 1 times something equals the Y value. Because I told you that all of these 4 points do not lie in a line, this system here is inconsistent. So we're looking for a least squares solution. We're not going to do it any different than the way that we just did the previous one. We've just switched it around. So X is our new A, Y is our new B, and beta has taken the place of X. So we're solving this equation here. Once again, this matrix here is invertible, so there will be a unique solution solving this system here, and it'll simply be that beta is the inverse of this multiplied by this, and we get this matrix here, 23.72, 6.4483 to a few decimal places, and that means the line of best fit, the line that is as close as possible, is Y equals beta naught plus beta 1 times X. So I want to point out, if you plot these, they will not look anything like a straight line. Remember, I told you that we actually fitted a cubic to this. I don't know why there's this obsession in statistics, and particularly in things like psychology, sociology, where they always want to fit a straight line to a set of data, even if it's not linear at all. In real terms, if we got data like this, there's no point fitting a line to it. But I just wanted to show you how we do those calculations anyway. You should plot the points, look at the data, and see if it looks linear. But there is a good thing with coming up with an equation that links the X and the Y values, because this equation here will allow you to predict what a Y value is going to be if you know the X value. So, these could stand for anything. Y could be someone's blood pressure and X could be their age, and this equation would allow us to predict their blood pressure given their age, or whatever it is. So it's a useful idea here, but we've got to make sure that if we're going to use linear regression, the data actually lies in a line. Now, since this doesn't, it looks more like a curve, why don't we try fitting a quadratic to this data? So we're going to take these same 4 points and fit a quadratic. As I told you, these 4 data points are a cubic. So a cubic's the best fit. Quadratic's not great, but it's better than trying to fit a line to this data. So just to show you how we'd go about it, I want to choose a quadratic that's of the form y equals beta naught x plus beta 1 x squared. So this has no constant term. In reality, that isn't going to make this better, but I just wanted to show you how we do it, because when we set up the matrix this time, there won't be a column of all ones because there's no constant term. So what we do is we set up our matrix X. So in the first column is going to go this. We want beta naught times X, so we just put the X values of -4, -2, 1, and 3. In the second column, we want to account for this. So we're actually going to put the x squared value. So -4 squared, -2 all squared, 1 squared, and 3 squared. If I wanted to add a constant term to my model here, I'd have another column of all ones. And I can do as many as I want. I could add another column for, x cubed terms. I could add another one for x to the power of 4 terms. That's polynomial regression. So I can keep going as much as I want. I just won't in this video because I don't want to bore you to death. So we've got our matrix X. Once again, beta is the thing we're trying to find. We're trying to find these two coefficients, beta 0 and beta 1, and Y will be the matrix of the Y values. So we're going to get a totally different answer this time, even though there are only two coefficients, beta 0 and beta 1. So we're not going to do anything differently than what we just did. The difference is in the setup of the X matrix there, but we're still solving X transpose X times beta equals X transpose Y. So I've gone through and done the calculations here. Once again, we have an invertible matrix for X transpose X, so there will be a unique solution to this system. So this is what we would get for beta. You can probably use matrix calculator for this because it might take too long to do it by hand. And then what we end up getting is this matrix here. So the first entry corresponds to beta 0 and the second to beta 1. So what we have is that the quadratic of best fit that's of this form, remember I didn't include quadratics with a constant term, so that would be y equals beta 0 times x, so I'm just going to round it to 2 decimal places here, plus beta 1 x squared. Okay, so there will be no other quadratics of this form such that the sum of the squares of the distances from each of these points to the quadratic is lower. But usually to calculate the error, we just get a computer to do it. I'm not going to go through hand taking each of these points and finding the distance from the curve because I don't think such a calculation would be enlightening. And whatever the error term comes up with, you get the idea. It's going to be as low as possible. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.